You're shy.
So, okay. So, good evening, ladies and gentlemen. This evening, we are happy to have Michael with us. Michael Fabi is a doctoral researcher at UFPA here in Brazil. So he's going to talk to us about his research. And after that, we're going to generate some discussions. So please stay tuned. Let's welcome Michael.
Ok, boa tarde a todos. Eu nome é Michael Fabi. Primeira coisa, só quero apresentação sobre meu doutorado. Então, depois, você pode perguntar mais sobre genética molecular. Entendeu? Entendeu? Ok. Vamos lá então. Desculpa, vou falar inglês, porque não entendo português muito bom. Pode ser?
Pode ser.
Okay. Alright, so the topic is integrating AI in the development of diagnostics assay for malaria.
Is that just let me keep one of them.
Continue.
Okay, so I'm going to be guided by this outline. I'm going to look at malaria, etiology, life cycle, a little bit about the pathogenesis, and I'm going to talk about epidemiology and some advances in malaria research, especially those ones that has been done in the lab aqui in Brazil, no Brazil. Okay, so what is malaria? You know, we've been talking about malaria since we began this workshop, but I'm just going to talk a little bit about malaria. So the word malaria is an ancient word from the Italian language, and it was actually coined from two words, mal and aria, and the mal means bad air. And unfortunately, the word malaria is already losing its right pronunciation, especially in English. But fortunately, we still have some languages like Portuguese that retain the right pronunciation of the word malaria. So in the course of this presentation, I'm going to be mentioning malaria, now malaria, okay? So it actually means bad air, and it was referred to as bad air because people that are living beside marshy area are the one contracting malaria back then. So that is why it is called malaria. Okay, so malaria, it's a protozoan disease caused by Plasmodium parasites. And this parasite is transmitted by the female Anopheles mosquito. You know, we have the male and we have the female. So when a male mosquito bites you, you ain't going to get malaria. You can only get malaria when a female mosquito bites you. So yesterday, Dr. Deborah presented a little bit about the epidemiology, about a little statistics about the cases of malaria all over the world. And in 2021, the World Health Organization talks about more than 3 billion people all over the world that are at risk of malaria. And these people scattered across the globe, in America, some parts of America, almost everywhere in Africa, and some other area in the Mediterranean and the Pacific. So malaria is indeed a great menace that researchers need to look into critically. So this is a bar chart that talks about malaria in Africa. You can see Nigeria, it's Nigeria is having the highest figure compared to countries like Chad and Zambia. However, before you begin to judge Nigeria, could it be that Nigeria is so plagued with malaria? I also want you to think about the population. In all of Africa, Nigeria has the highest population. You can expect, if with this figure, compared to other countries, we can say, well, I feel they are doing a little bit well in terms of how to eradicate malaria in Nigeria. But this is just a bar chart that shows the distribution of malaria cases in Africa. So we also have another one from America. So according to Statista, where I got this information, you can see Brazil here, 27%, Venezuela, 28%, compared to countries like Bolivia. However, the majority of the malaria cases in Brazil is in the north parts, states like the Amazon. That is why people in the south, sometimes they don't even have any cases of malaria. When I came to Brazil last year, I was having a fever because I was exposed to mosquitoes. So the first thing that came to my mind was, definitely I'm having malaria. So I went to the hospital, to tell the doctor, you know what, I'm having malaria, can you just give me some prescription? And the first thing he said, are you sure you're having malaria? Okay, the doctor was, what do you mean by malaria? Like, there's nobody comes to the hospital to report malaria, even though there are mosquitoes everywhere, right? So I told the doctor, these are the symptoms I'm having: headache, fever, during the evening, I begin to shiver. During the day, I could be well, but in the evening, I'll be shivering. So I told the doctor said, well, we are going to give you some prescription, but it's not sure it is malaria. So what I'm trying to drive home here is that in Brazil, we have mosquitoes, but we have little report cases. And later on in my slides, I'm still going to be talking about the types of mosquitoes that causes malaria in Brazil, and this is one of the reasons why it is not reported, because it is asymptomatic, right? All right, blah, blah. Okay, so despite all these things that I've said earlier, does that mean that some countries are not eradicating malaria? No, some countries have been eradicating malaria as far back as 2000. Year 2000. Some countries like Egypt, these are the countries that has been eliminating malaria. So these countries has been declared malaria free. Okay, so I believe that Brazil is also in the process of being declared malaria free. But a lot of work, a lot of research still needs to be done, especially in the Amazon parts where there is abundance rainforest. Okay, so I'm just going to talk a little bit about the two patterns of how the transmission pattern of malaria. So we have the stable, which is common in the Africa, because over the years you will see cases of malaria being reported at the hospital. But we also have another transmission pattern called unstable or mesodemic pattern, and that is what is found in Americas, especially in Brazil, Venezuela, because there could be a surge this year, the next year there might not be any cases, right? So this particular pattern is called unstable. So sometimes people kind of wonder, are you sure there is malaria in this Brazil? I bet some of you probably have not been diagnosed, of course, you've not been exposed to. So we have majorly two patterns of transmission. We have the stable and the unstable pattern. Now, who is at risk? According to the World Health Organization, children from 0 to age 5 has been described to be at risk of malaria. Okay, this could be because they have low immunity. When a child is given birth to, as the baby is growing up, is developing more immunity, and that is why they are susceptible. We've been using the word susceptible since we began this conference. So this is why children age 0 to 5 are susceptible, because they have, they are still developing their immunity system. So there are also some factors that can predispose somebody to malaria, and some of them include age, ethnicity. I think from this last workshop I heard Professor Awe talking about age. Age could be a predisposing factor. As we are growing older, the immunity is going down, right? So when someone that is like age 70 is exposed to mosquito bites and mosquitoes that are infected, the person can easily come, with malaria. We also have ethnicity. In this case, I'm going to talk about research has shown that there is a particular mutation in the genome of some people of certain ethnicity that made them to have resistance against malaria. So even though when an infected mosquito bites them, because of the mutation it carries in their genome, they are just going to, they won't have malaria. So another thing is pregnancy. Pregnant women can easily, come up with malaria after being exposed to mosquito. Then we also have socio-economic status. People that can't afford decent lifestyle. For instance, somebody that can't afford to buy mosquito nets, repellents, they might come up with malaria when they are bitten. Then we have immunity and we have rainfall, and that is why it is abundant in the Amazon in Brazil, because there we have like abundance rainfall. Almost every day it rains in the Amazon. So what are the control measures? We have different control measures. We have the biological, we have the chemical, then we have some other factors that have been put in place as control measures. But I want you to pay more attention because we are just getting into the presentation. So what is the etiology? Research has shown that we have more than 200 parasites, right? That we have more than 200 mosquito parasites, but not all of them can cause malaria. The ones that can cause malaria are just 6. But there's an argument over the 6th one, so that is why I didn't mention it in this place. So the one that is known generally is falciparum, Plasmodium falciparum, Plasmodium vivax, Plasmodium ovale, Malaria, and knowlesi. However, out of these 5, research has also shown that falciparum has the 92% of causing malaria, okay? While the rest 8% is divided between vivax, ovale, malaria, and knowlesi. But I can bet it with you that vivax has the highest percentage within the remaining 8, right? Pamela. Okay, so this is the map of the world showing the distribution of malaria parasites. Here is America, right? So we have vivax, we have malaria. These 2 parasites can only infect human, while these 2 can infect both apes, monkey, and human. And that is why I didn't want to mention this, because you can't find them in everywhere. While here in Africa we have falciparum, we have vivax, we have ovale, we have malaria. So you can begin to think, could this be the reasons why there is high incidence of malaria in Africa? Because we have a whole lot of the species that causes malaria are key in Africa. Okay, so within the Mediterranean path, we also have some species like vivax, ovale, malaria, knowlesi, but this particular 2 only infect monkey. This one infect monkey in this region. There is no literature that says Schweitzer and Rodini has infected human. Okay, but here we have Seminole and Brazilianum. These species, they can infect monkey and they can infect human. But there was a particular research that says even though they infect monkey doesn't come up with malaria. So this could be because of the differences in our genome. But let's go. Now, it's getting more interesting. I think it is important for us to talk about the difference in the aspect of the molecular biology right now. It is important for us to talk about what is the difference between Plasmodium vivax and Plasmodium falciparum, because these are the two parasites that can cause and these are the two parasites that has been recorded over the years. So I have key features that I'm just going to use to describe it. And the first one is the red blood cell invasion. You know, when an infected mosquito bites a healthy person, right? If the mosquito is infected or has the vivax parasite within its guts, the vivax, the mosquito that is carrying the vivax in its guts, can only infect the CD71 reticulocytes. No, this one is not a red blood cell, although it's a precursor of a red blood cell. Okay? And another thing is that the lifespan of this particular blood group is very short, between 1 to 4 days. But if it is falciparum, if an insect bites somebody, okay, and the insect has falciparum in its guts, it can stay in the body for a very long time, like 70 days, because it takes like 70 days for erythrocytes to degrade. So it has a lifespan of between 1 to 70 days compared to reticulocyte, and that is one of the reasons why Plasmodium falciparum has been recorded over time, because it will take a long time for it to remain in the body, while in reticulocytes it takes shorter time. The another key feature I would like to talk about is the genetic culture. In the lab, it is very difficult. You can't culture vivax, but you can culture Plasmodium. But
a very fast question: why this happens? Why he remained so long in the body?
yeah, because it takes between 1 to 70 days for erythrocytes. You know, erythrocytes are red blood cells. They are produced in the bone marrow. Okay, so they move from the heart, circulate in the body, and it takes 70 days before they degrade. So if somebody has been infected, right, the parasite is going to be in that blood. You can imagine the parasite being in the body for 70 days, compared to if the parasite is in the body for, say, 3 days. So if somebody is infected by vivax, right, vivax cannot infect erythrocytes. Vivax can only infect the reticulocytes. So if reticulocyte is having a lifespan of 1 to 3 days, if reticulocyte is dying, that means vivax is also going together with it. I want you to picture a situation where an host, take for instance, this guy here is an host. Then this guy is an infection or a disease. If this guy infects this guy, right? But this guy just has 5 days to live. If this guy dies, what happened to this guy? He dies too. So exactly that's what happened. So reticulocytes only have a lifespan of 1 to 3 days, and vivax can only infect this. So if reticulocyte is going off from the body, it's going away with. But erythrocytes can stay for 70 days. So that is more or less like 2 months. And the incubation period for Plasmodium falciparum begin after 16 days. So definitely it's going to be expressed or seen. So another one is the dynamics of transmission to mosquitoes. So just like I explained here, they live for a very short period, while this one, they can live for a very long time. Long-lived gametocytes, which I'm still going to talk about a little bit in my future slide. Then we all know that mosquito or malaria has shown a kind of resistance to drugs. So there are different targets when they are making drugs, when they are producing drugs. There are different targets that they look at in the body, and they don't have the same targets. So vivax has shown resistance to chloroquine, sulfadoxine, and pyrimethamine. While like 3 different drugs, it has shown resistance. While falciparum has shown resistance to almost 7 different drugs, including the popular artemisinin derivatives. Then we also have the molecular mechanism, which is very, very important for me to mention in this presentation. So when drug is about to be produced, we look at different regions in the body, different genes that could be the target. You don't just produce a drug without you having a target. So this has been the target when they were producing drugs for Plasmodium vivax. But in the case of Plasmodium falciparum, there are different regions, there has been different targets, yet there are mutations that makes them to be resistant. Blah, blah. Okay, so here I'm going to talk a little bit about the life cycle of Plasmodium parasites. So the life cycle involves 3 stages. I'm going to talk about here where there is no figure, then I'm going to show you the figure. And these 3 stages is divided into 2, the one in the host and the one in the mosquito itself, which is the transmitter. So the first thing that happens is that when an infected mosquito bites an healthy person, right, it releases a substance that is called sporozoites. Now these sporozoites move in, and if it bites at this region, it moves with the help of the blood that circulates, and it's targeting one place. It's not just going anywhere yet, it's targeting one place. And the target is the hepatocytes, the liver parts. So in the liver part, it's going to stay there and taking some rest. And while it's taking that rest, at that stage, that sporozoid is called schizoids. Okay? Now, over time, this schizoid is going to burst. And when it bursts, it's going to lyse. If it lyses, it's going to release something called merozoites. So these merozoites right now, they will stay within the red blood cell. Okay, especially if it is from falciparum. So they're going to stay in the merozoites. So they can begin their own by producing another gamete, continue the life cycle, and they can continue like that, or they can form what is called merozoites or inozoites, and that is when you can begin to see symptoms, because it is possible for somebody to carry the parasites and without expressing any symptoms. Okay, so the life cycle can continue like that. It can continue from here and come this way, then come to this part, then start again, and it can also continue this way. So if it goes this way, that means there's going to be there's going to be symptoms that will be seen. So the what is it called? The inozoids can also be picked from the body of someone that has been infected by an uninfected mosquito, and that is where it's going to complete the life cycle. Right. So there's a particular slide that I'm still going to talk a little bit about the kind of research that is being that is targeting this part, just this part. Okay, so like I said, this life cycle is divided into 2, in the human and in the mosquito. And this is the point at which a mosquito is biting human. So this mosquito, this red part means this mosquito is infected and it's releasing these sporozoites. The sporozoites move into the liver cells, and from the liver cell, it's form a schizogony. And the life cycle can continue here until when it bursts. But if it doesn't burst, it continues like that. So if it comes here, another mosquito bites and pick it up, and the cycle continues. That's not all. Let me talk a little bit about the pathogenesis. How do we come about disease? How do we come about fever? How do we come about headache and what have you? Which are the symptoms of malaria that we have been talking about? So this particular cycle can continue, but if the cycle at this point, if this red blood cell lyses, if it breaks, it's going to release some particles. So this is the red blood cells that I brought out here. So it breaks. So as it's breaking, the schizogony, it releases the merozoites. These are the merozoites, okay? And normally, when something strange happens in your body, the body is going to respond, right? Very good. So the body right now, so when it breaks, it releases some toxic waste products. Now the toxic waste products are called emezoins. Now the body triggers a host of immune response. Come on, we are having some intruders. Go and fight. So when the body is triggered, it releases some immune system. And these immune systems, some of them are cytokines. What they do is that they are going to cause inflammation. And inflammation is what makes us to have the headache, the sneezing, all the symptoms that we have as a result of malaria. Okay, so these are the headache, fever, vomiting, what have you. Which, if they are produced, as they are being produced, the body is also producing white blood cells. As this result has been produced, the body is also producing macrophages, which are the white blood cells, to attack them. So over-secretion of white blood cells can also lead to so many things. It can lead to cancer. So you can imagine what malaria can even lead to. Blah, blah. Okay, so these are just the symptoms of malaria. If it is the mild one, and if it is in the severe cases. Now, this part, I'm beginning to enter into my area that I just want to talk about. So we have different methods of diagnosing malaria. Some of them are conventional. Some of them have been in existence before I was given birth to, and some of them are just coming up, right? So we have the conventional and we have the recent or current trends. So some of them include thick and thin blood smear, rapid diagnostic test. During the COVID, everybody were using rapid diagnostic test where your antigen will be used. And we also have serology with ELISA, and we have polymerase chain reaction, which is PCR. And we have different types of PCR. So we also have challenges. So this is where I'm trying to pick my research focus. What are the challenges that we are having? Because our inability to detect malaria is also causing problem. So, because it is something that you know, that you can tackle, that you can face, right? If I don't know something, I'm ignorant. But when I have the full knowledge of something, I can plan myself on how to tackle it. So we have limited diagnostic tools, we have drug resistance, and we have asymptomatic infections. There are some regions from my previous slides where they don't show any signs, they don't have any headache, they don't have any fever, there is no shivering, yet there is malaria parasite, right? So in these cases, they are asymptomatic. So like I said, we also have limited diagnostics tools, especially in some places in Africa, where we don't have sophisticated tools, to diagnose malaria. And the ones that they have, they are not efficient. Sometimes they come up with false negative. In the cases of parasystemia, where the diagnostic tools is not being able to detect a lot of parasites in the body. So these are some of the work that has been done in my lab aquí, Brazil. So the first thing that's one of the works towards malaria was to create a detection method, through PCR, because it is believed during COVID, PCR become a gold standard because it can detect so many of the viral particles in the sample. So PCR2 can also detect a lot of malaria parasites in the body. But something has to be taken note of here. So they don't just take sample from the body, they used the mitochondrial DNA. And do you know why? The reason is because mitochondrial DNA has a conserved genome. A lot of things can happen to our genome, like mutations, right? So if all part of the body is carrying mutation, it will take a very long time before it can happen to the before it can happen to the mitochondria. Mouse.
Mouse.
Oh.
Mouse.
Mouse. Okay. Okay, so I said because the mitochondria is a very conserved region, so a lot of it will take a very long time before the mitochondria can acquire mutation. So that means if we use the mitochondria of the parasite, that means we can easily detect it, right? So that's why they use the mitochondria. Even in DNA, you will recall that in meiosis, there is usually what we call recombination. If there is a recombination, one of the parts that don't usually undergo recombination is the mitochondria, and that is why mitochondria. And this is another research that was done, not in my lab, but somewhere. But it is noteworthy for me to mention it also in this research because one gentleman, I think this bro, was asking a question the other time that is there a way we can suppress or something like the population, get rid. So in this particular research, what they do, since we all know that the species or the sex of the mosquito that causes malaria or that transmits the parasite that causes malaria is the female. So what they did is to see how they can suppress the female. So in the life cycle, so I'm going to get there. So this is what happened. So what they did is to cut off using CRISPR. CRISPR is a gene technology that you can use to, cut off some region in the DNA. So what they do is to cut off the gene or the allele that leads to the femaleness. So at the end of, in these parts, okay, this is when, this is just like a gametocyte. You don't know maybe it's a female, you don't know maybe it's going to be a male. So what they did is to look for the allele that is going to make that egg to become a female, right? So they did some genetic engineering to it, such that at the end of the differentiation here, here this is the egg, and there's going to be like a differentiation. We have the male and we have the female. So eventually, if any one of them form and it becomes a female, it will eventually die. Okay. So if this research was published last year, so if there is like a more impact on this kind of research, I believe it might also lead to eradication of malaria in the society. So this is the point at which CRISPR-Cas9 was implemented, and it leads to the death of the mosquito. So what are the research gaps that we still have in malaria research? One of them is CRISPR technology. There is still need for more works to be done in CRISPR. We have nanotechnology application that we can use to improve detection, and we have biosensor developing rapid point of care. Then these parts which align well with my research focus, integrating AI in the development of diagnostic assays for malaria. And I was asking myself some questions since I have these particular research gaps. So what am I going to do right now? It has been like a questions that I've been pondering over time, and I'm hoping that maybe by the end of this conference, I will have a deeper or a better understanding on what I can work with my PhD. So, but right now what I'm doing is I'm exploring the intricacies of mitochondria. You will recall I told you that there is a particular work that was done in my lab, but the work was on Plasmodium falciparum alone. And we have 5 species that can cause malaria. So I'm trying to develop a primer that can target each one of them. What I've seen so far is that the conserved region, when we look at the genome sequence of all the 5 species, the areas where they differ, they don't align. So the difference in Plasmodium can be in these parts, right? In ovale, it could be in these parts. In malaria, it could be in vivas, so it's scattered. So we are trying to use some bioinformatics pipeline or tools to, develop a primer that will be able to pick such. And one of the things we want to do is that if this assay, like if I extract a DNA from any mosquito, I don't know the species, if I use this assay, this primer, it will be able to tell me the species, right? If it is malaria, if it is what have you. Then integration of AI into LAMP. LAMP is an example of a PCR, polymerase chain reaction, and it is called loop isotimer amplification, right? So it is not like the conventional PCR. The conventional PCR uses two primer. Primer are what can help the machine to detect what you have in your tube. But in this lab, it uses 4 forward primers and 4 backward primers. And it can also make the diagnostics to be very effective, okay? Detecting what you want to detect, it can make it to be effective. And another thing I'm considering doing after all is to, of course, enjoy my life, okay? But just before I began to think of how I can begin to enjoy my life, I'm beginning to see some problems that are, looking at me face to face. And some of them is what we have been discussing since the beginning of this conference, and it is how I can integrate artificial intelligence into detection of malaria parasites. So this is one of the works that has been published. So basically, the blood smear from the slides, where they take the picture and they were annotated, and they compare them to what technician will do, right? So they take the picture, and it undergo all these things that we have been talking about: the training, the cleaning of the data sets, that will eventually leads to like something that can be able to detect malaria without you going through so many stress, without we even using PCR. Because for you to use PCR, you have to take the sample first and come to the lab, work on the process of PCR can take like if it is 40 seconds, it can take like 1 hour, 1 hour 30 minutes, depending. Then I'm also looking at another methodological framework where I can combine LAMP, the loop that I mentioned, the loop amplification, such that if in Africa, for instance, if I go to the field and somebody is having malaria, if I collect the sample and the sample is put in the tube, after adding like an assay, I can just detect maybe by color change, right? I don't have to subject the sample to excessive or eye diagnostic. So by just putting the sample in a tube and adding the assay, it will just show like a fluorescence that is just going to reveal a light. So that is another part I'm looking at. So in this particular work, what they did was they took all the data sets and they were processed and they were annotated. And the data sets were captured by YOLO V version 8. This particular, should I call it model now? This particular one here is just like a camera. It's just like a capturing device. Okay, there are different versions. It starts from this YOLO is an abbreviation of you only look once. It is not you only live. It is you only look once. So it captures an image and it is very powerful. A lot of all the Tesla, this is what they use. The cars that drives themselves without nobody driving them. This is the version that they use. And if you are also planning of doing, coming up with an algorithm or a model that will involve you to integrate a camera, you can also think of YOLO version 8. There is a version 9, but literature says that version 8 is more effective. And they come up with a model that was compared to what experts did, and they realized that it is more efficient. Okay, so like I told you, one of the reasons why I'm in this workshop is for me to also improve myself on how I can come up with something like this that can be effective. Now in this work, this is what they did. They took a picture. This is like a red blood cell, and this is the leukocytes. This is malaria parasites, and this is another image that doesn't have anything. So the machine was trained to be able to differentiate these two images, okay? And so it can be, used to detect malaria parasite without, going through, without going through high cost diagnostic tools. And they also, of course, they did so many what's it called, machine learning, deep learning work to come up with the results. So this is the area where they were annotating the images, trying to compare an unhealthy red blood cell to if something that is not healthy. So because these are what they're going to train the machine to be able to detect, and eventually it will be able to work well. So not only that, I heard somebody talking about there will be need for you to get many samples of healthy picture, or many picture of healthy samples and many picture of unhealthy samples. So look at this one right here. We have A, B, C, and all of them are healthy, and the computer has to be able to detect, so it doesn't have to just be one particular one. So in conclusion, effective control demands a thorough understanding of transmission and diagnosis. So leveraging artificial intelligence and machine learning offers a promising approach to bridging this gap. So I would like to, of course, appreciate the Sally, the Ahmed, the Unicamp, and this is my school, my lab, and I'm in Brazil because of this organization. So I want to thank every Brazilian here. Thank you so much. Obrigado pela sua atenção.
Thank you very much for the talk, very nice talk. Some question or comment? Could be in Portuguese.
Hi. My question is, in the last slide, you show us some pictures and to the computer to analyze them. You in machine learning, you use neural network convolution.
Yeah, convolution neural network.
Okay, it's just that because I was wondering that for it to analyze it would be it, but I didn't.
Convolution CNN was used, and it's
Oh, okay. Thank you.
and it was, this particular one is a different research, and this one also is another different research. But both of them, they all use convolution neural network before they convert. Yeah.
Because it can cater for images, can cater for both structured and unstructured data. So those are advanced models, machine learning models. Different from all the support vector machines and the random forest, and so these are neural network models.
I think they are under deep learning, right?
Deep learning models, yes.
Thank you, sir. Thank you very much for your question.
Any other comment? Question? Okay, let's clap for So, thank you, ladies and gentlemen. I will see you tomorrow. Have a wonderful evening.
All right, thank you, sir.
Thank you.